Okay, so um, in this lecture we'll finally start the C++ part of the course, where we will be looking on the C++ uh, language in detail. So we create a new project, call it so the most important difference between C and C++ is that C++ is fully object oriented, so we can create very nice, very complex self-contained objects that can allow us to structure code much more elegantly than how it is possible with just C. So you might remember in just C we can use the structures, but then we still need to have individual functions to which the structures needs to be fed and so on. So it's not particularly self-contained, and also we can only use normal simple operations on our variables. With C++, we can define own operators for the new types that we create as classes, so it is quite a much more advanced mechanism. So let's see how we do it. In principle, you can create a class like we did with structs in the same file you are writing the rest of your code, but of course, since the idea here is to have a nice structure and not too much too large files and too much spaghetti code, we usually create two files, or depending on if it's a template class, one file for our classes. So let's do that. There is this wizard tool that we can use here, but we could also do it completely by hand. Class, we give it a name like C, let's call it C my class, for example. And it's customary to start class names with the letter C, but of course, like any naming convention, it's completely arbitrary, so you don't have to do it. You can just call everything my class or something else. For example, the Qt framework starts everything with a Q, so that's that. So here for the file names themselves, we drop the prefix, and we don't specify anything else. And when we take a look what happened is it created for us two files. Let's create a new filter. So that we have the files all together. In C and C++, it's kind of customary to have headers in one view and the source files themselves in another view, but this is kind of a bit inconvenient. I prefer to have the files which are related together. So as you can see here, we have a class. It looks pretty much like a struct, just that it's called a class, and of course it's much more capable. One thing to be noted is that when you are using CPP files or C++, you could in principle define a struct and give it all the features of a class. This would of course then only work with C++, not longer with C, and it would have only very minor differences in behavior, but of course normally it's recommended to make classes as classes, so we do that. And in the source file for our class, currently we don't have anything. We just have the include so that the file sees our header. And so classes have many properties that are new that you didn't have in standard just C. And one of them is that you can define what is allowed to access individual members. So in C, since you don't really have any sort of hierarchy, everything is just public, so any function can access any member of your object. In C, the the whole idea is that you can define properties as protected or private, so that they will be handled by your internal functions, and then you only expose a certain defined public interface to your class, and a user of this class then doesn't get the opportunity to mess with some internal states which should not be directly edited. In a class, by default, everything that is defined on the class is private. So if we just add a variable, let's say int m underscore my int is equal 0. Oops, so we had this, and it is kind of customary if you have objects. Since we have functions, then within the objects which implicitly see the content of the object, it is customary to add a prefix like m underscore, indicating that this is a member of your class and not a local variable. Of course, like all the naming conventions as mentioned, this is fully optional. You could just define it like my int or just underscore in something. So this is not enforced in any way. And like with structures, of course, well, first of all, we need to add an include. We need to see this header, so my class h. This we don't need. Yeah. And see my class. We can just instantiate it like we would instantiate a structure. An important feature is that we can use such initializations here now with C. We kind of the class, the structure with C, the struct is just a piece of memory without any own internal intelligence, so to say, without any code. It's just the data. With C++, objects get associated so-called constructors and destructors. These are code pieces which are invoked when the object is created or destroyed, and thus we can also add such default initializers, which then will be part of the compiler generated constructor code. So if we just write here, it is my class, and if we have, of course, set the value to a defined value, then if we put a breakpoint here, we will already see that the object does not contain any garbage, but it contains the value we have initialized it with. Of course, 0 is a bit boring, so we could also initialize it to, let's say, 1, 2, 3. So as we see, this already shows us a certain level of automation. With just C, you would need to create your struct, and you would need to call memset, or if you want something other than 0, you need to have some function, and then you would need to explicitly call that in, like for example, my struct init, my struct1 underscore init function or something like that. So here we already see that we are saving on code lines, which is very useful. Let's set this back to 0, and let's now see what if we can access something of this thing. So let's say int my int is equals, oops, should be an underscore, and it shows us my int, but it shows this small log symbol. And if we try now to compile it, it will not work, and it gives us an error message: cannot access private member declared in my class. So while it shows us what is there, it doesn't allow us to use it. If we want to access something that is well, private, or well, if we want to access a variable member, then we need to define it either as public, do it like this, using the public keyword followed by a double point, or there is also a different type called protected. How this works, I will show you in a second. For now, let's just make this public and run it again, and now we see that we can access this variable. Of course, this limitations defined by members being public or private is only something that applies compile time, so it is not in any way enforced in the code. We could just knowing the structure, just go to the memory. So we can maybe actually do this. Let's set this to 1, 2, 3. Let's comment out our public thing so that this again doesn't want to do, and then we know that this thing, the way it's structured, it should have nothing else but just the integer. So we can just grab its memory, and voila, we were able to access the value. So it's not like the private or public keywords enforce anything really in runtime. They don't. They are just to ensure that you can structure your code, and that the structure you gave to your code will then be enforced, so that you don't accidentally act against your prior intentions, so to say. Okay, so let's go back to make this public and get rid of our dirty hack. Now, of course, this is convenient, but often might not necessarily be what you would want to do, because as said, the idea is that you can use this variables, this let's say protected or private variables to as an internal state, which might need some level of complexity to be updated, so that it's not something that you just simply update by setting a value, but you need to change some things, calculate a new value, modify multiple other variables. Maybe you need some level of consistency. So the way you would normally access such of course for reading it's kind of not so critical, but of course for setting, if this thing would be still public, we could then still set this to 456. Of course now it's complaining because it's already protected, but the whole point is that we would want somehow a more formal way of accessing those things, and usually this is done using a setter or getter function. So void set set my int my int and then we go to the header. So in principle, in the header you only define your variables, you define your functions, you don't write code itself, you write only definitions. That said, with C++ you can write code here, so in principle this works fine. You could just write a short piece of code directly inside of your header file. This is, however, not recommended with regard to having the code nicely structured, and also with regard to compile time. So it usually you would have all your code in the CPP file, and then of course you need somehow to say that you want to write the body for this function, and you are using here this double dot operator. So you have the class name, then you have two double dots, and then you have the function name, and this will be that function. And inside this function we can access all the variables defined on our object as if they would be as a local variable or like a global variable, that they are available in this scope now. In principle, if you would need to access the memory of your own object, you can use this variable, which basically gives you the memory to the object this on which this function has been invoked. So you could also access variables like that, but of course for convenience this is not necessary. You can just do it directly. So we would have a setter function, and for example you could enforce a certain value range. So let's do that. We give it a return value, and now we will return true if we do something, and here we can have an if this is less than 0 or is greater, I don't know, 10,000, then return false. So we could have, for example, a function here which takes some value that you want to be set as my int internally, and it will enforce that the value must be 0 or less than 10 or less equals to 10,000, and if it is not, then it will even give you indication with the return value whether it has performed the operation and set the variable, or whether it has bugged out because the provided argument was invalid. And of course you could also use some, for example, an integer as a return value, so that you have an indication if it's a more complex error state, like what was the error. In that case, the logic here would be slightly inverted. Normally if you use bool, then of course if you return 0 it's a failure, if you return non-zero it's a success. But if you would have an integer as a return code and you would want to be able to communicate return states, then the logic would be normally that 0 indicates success and non-zero indicates failure, and the value actually indicates what sort of failure occurred. Although that said, this mechanism of handling return codes of course would be the same just in C. So just to set this, and then of course we would want to read the variable as well. So we make an int get my int. We can define it as const. Defining a function as const means that this object inside the function will also be const, meaning that we are not allowed inside the function to set anything. So if we would try to set this to, I don't know, 0 or something, it will bug out telling us that we are not allowed to do it. But if we want to read it, for example, to return it, then it's completely fine with that operation. And as said, this is just a compile time enforcement. It will not affect how the code will look generated by the compiler. So here our logic to this would be set my int, and then here we would use punct get my int, and this already demonstrates also how you call functions on your class. You just use the dot operator. Like with structs, you use dot to access member variables. In generally, dot is used to access members, and the member can also be a function. And then you can call it, and that's that. So we can of course run it to see how this works. And as we see, we can just read the value without problems. So at this point it's worth taking a look how this function call looks, because if we think about C and our machine code, there isn't really an obvious mechanism how the function would know to which object it belongs. So it's obvious that we need to somehow communicate that into the function, and this is done in a pretty simple way. When we take a look on the generated code, we see that we use again two registers to pass arguments, but we see here that we are passing 2 arguments even though we only have 1. And this 1C8, that's just our value here. So we see the second argument RDX is just our value, and the first argument, which we don't see here, is then passed with through RCX as usual, and it is passed with it receives the address in memory where our object lies. So it's a bit like the mechanism that you had when you wanted to return a structure from AC function. Since you cannot return a structure in a register, what the compiler does is it prepares some memory for the return value on the stack, and then it gives the pointer to that memory as a first argument to the function, and all the other arguments are then shifted by 1 within the calling convention. And the same thing happens here. And of course, if you would here return again a structure or a class as a return value, then the whole thing would then shift by another argument. So this is generally the mechanism how this works. It's quite trivial. Of course, you could write something similar in just C, that you would, for example, have your class, and then you would have some function pointers on that class. These function pointers then would take, you could call them directly, and then as first argument you would again put the class name, the variable into it. So it would be something like this. And as you see, it's of course more typing and not as convenient as when it's done automatically. Plus, you don't have any of those nice protection features. So here you see how those things work. We can of course create such a class not only on the stack but also on the heap. So let's do that. My class asterisk pay class, but we of course need to now somehow create it. As you remember, if we create just a pointer, the pointer is just an integer of the native bitness, and it does not as such create any objects. So one way of course would be to use the malloc operator, but this would only create us a memory block. But as we have said, the class here has some additional code which does the initialization, and also which would be called during the object's destruction. In this case here, we don't have anything to be done on the destruction, and the object gets destructed just when we leave the scope. But of course, when we create this object as a pointer, we would not want to first allocate memory and then manually have to call the construction code. So instead, there is a new operator called new, which just takes the class type, and it will do both things. It will allocate memory and it will call the initialization code. So we can run this and then observe that here we have an object created with our initialized value. We should maybe really keep this just always 1, 2, 3 so that we see that this is correctly done. Voila. And as you might remember from our lectures about memory management, after you are done using some memory, you need somehow to release it. And here, since as I mentioned, there is code that wants to be executed on the object's destruction, we also cannot use just free, because free would just free the memory without doing anything. There is a new keyword called delete, and what delete does is it will call the destructor code for this object and it will unallocate its memory. So after we have called delete, when we look inside our memory, the thing is kind of so the memory is still readable, because as you remember, the heap manager is giving out memory from a larger pool. So if we free it, it will just only be marked free. It will not automatically become unaccessible, but at least we see that if we go to the memory itself, that will be filled with oh, actually it's unreadable. Okay, then in this case it was completely removed. So if it shows question marks here, then it means that the memory is not readable at all. But of course one could still try to do such a thing here, and let's see how badly this fails. So if the memory really right, we should give this a new name or not define it. Let's do like this. And in this case, we are even we are triggering a access violation, since the memory, in fact, became invalid, not just zeroed, but invalid. And then, of course, this is a bug, so such a situation should be avoided. So after we have deleted something or freed the memory, it is customary to always set it to null. Although in C++ there is a new keyword you can use, nullptr. Functionally it does exactly the same thing. When you compile it, it just sets it to 0, but it looks nicer, and with regard to automated mechanisms to detect potential issues, it is recommended for newer projects to use this nullptr. Okay, so now before we proceed to next things, let's see this code that I mentioned. This is the one that is invoked whenever an object is created or destructed. So here, of course, we can put a breakpoint and see how far we go when we click through the whole thing. So here internally there is some code which actually just uses malloc to create a new code block, and then we have here some moves, and then we have a call which brings us to a code which has like a class name, double point the same name, and then it contains the instructions. Basically is a function which will initialize the variable to 1, 2, 3. I think 7b is what is 1, 2, 3. Does it show us? No. X7b is 1, 2, 3. Yeah, and at this level, of course, this code is completely compiler generated. We only have told what we want as a result. But of course, when we are creating an object, we might have more special criteria how we want this to be initialized. For example, we might want to call a function to give us some new value or something like that. So we can explicitly create this function. And the function I mentioned that is called when the thing gets destructed, the destructor is class name prefixed with the tilde sign. So this is the constructor. And the nice thing about constructors is that you can have multiple, like with functions. In C++, you can have various functions with as long as they are different in with regard to the argument list, the compiler can tell them apart, and then you can use both on how you want. So here we can have a constructor that just doesn't take any arguments, and one which takes an initial value for our int. So let's implement those. So our destructor doesn't really have anything to do, and our two constructors, well, this one also doesn't have anything to do, and this one will set underscore to my int. This is one way of doing it. There is also a second way you can do the same thing. You can provide a initializer list. So we provide the variable names, and for next one we'll just comma separate the next one and the next one. And this mechanism is required if you have variables of a type that cannot be assigned. So for example, if you would say that my int my int is const, then you kind of cannot assign it, not even in the constructor, but you can use this initializer list to achieve the same result, it being then correctly assigned. So let's take a look how this works. Let's put a breakpoint here as well. So again, we skip the first call because, as said, this will just be the implementation of the. Why do we need this? Yeah, we need it. So this here will only create us new memory. We can get out of there. We don't want that. And then the next one here, as you see, we are jumping to our constructor and for a jump list, and this time we are ending up in our own code. But as you can see here, since we have not specified anything in the body, we here will still have some code which will initialize some things for us. Let's just see one thing. So this was 1, 2, 3. Yeah. So we can step through the code, and as you see here, it will do this assignment still on its own. So the code for the assignment is part of the automatically generated constructor. So that if we use this mechanism, we can, for example, have like a lot of variables which are just initialized always the same values, and then we could have some variables which here we would always initialize with some thing that gets changed from one invocation to the next. And then of course the thing returns, and then if we go to the delete instruction and step through it, we see that we are calling here the destructor first. So zack, let's get in. We have a body for that. We should have a body for that somewhere. Here. We need to go a bit further. Now we are where we want to be. So we are entering this function which basically doesn't do anything. It just well, all those code here is mostly like built-in checks. We could disable all of that if we want. Maybe we should do that so that the code looks nicer. But basically, it's called. The things are cleaned up. Whatever has to be cleaned up, at some point, you will then go to a delete operator implementation, which will then, once we step through it far enough, just end up calling free, or in this case, free debug, depending on whether it's a debug or a release build. So the things are getting more and more complicated, and a very important feature with regard to this is that if we go to our main class, we can use the destructor also with objects on the stack. Oops, not here. So we have our class created on the stack, and it will behave the same, but we don't need to tell it to delete. The delete will be automatically called as soon as the object goes out of scope. But we wanted to make the code a bit more, the machine code a bit more readable. So let's see what all useless stuff we can disable. Yeah, this should go away. And we could also disable all the runtime checks. And the security checks. And that should be good enough. That should already give us a much more readable code. So here, as we see, um, on the stack it's a bit simpler. We don't need to call the new operator because we already have the necessary memory. It will just load the right address into the first argument register, and then it will call the constructor of our class. And as said here, now you see the constructor is much simpler since we have removed all this unnecessary debug code. And then here when we have to be careful when stepping, because here as soon as so we have here this operation, and in the next lines when the curly bracket closes we have the destructor. So here we just step over it, and then here we just step into the destructor. Okay, and here we are. So as you see, it's quite simple. There is somehow one thing I didn't disable yet that makes this jump list. I think that was here. I think it was that thing. No incremental linking. Let's see. Step. Yeah. So now we are just ending up directly inside our function without having to take the detour through this jump list that is there. And yeah, and that's that. So such a destructor is extremely important because, as you know, when you might have to free some memory which you have allocated, and the destructor gives you the opportunity to do it. So you can use the destructor whenever you want, and to free things that have been created during the class's operation. So you don't need to call some cleanup function before you call delete. You can just delete it, and all the cleanup will be done automatically. So one example, of course, what one could use such a mechanism for is if you would want to have some nicer way of working with strings. As you remember, in using just normal C strings is kind of inconvenient because you need to know how long your thing will be, or if you don't, you might to add some manual mechanism to change the length of the memory each time you add something, so it's not very convenient. But you could create, for example, a class which represents a string, internally holds a C compatible string, but does all the bookkeeping about the memory allocation on its own. So you just have a function add to string format or whatever, and the string will always get grown whenever it needs to be grown, and as soon as you go out of scope, the string will automatically be then freed from memory. So such a class is provided, by the way, as part of the standard C++ template library. So a bit later, once we are done with the basics, we will take a look on all the at least the portion of the provided STL classes, which are very convenient with regard to writing modern C++ code. Let's also add some here a demonstration of using our other constructor. So as mentioned, you can have multiple constructors, only differing in which arguments they take, and then just by providing or not providing those arguments, you can tell the compiler which particular constructor to pick. So here we now said we want to use the second one, and if we step into it, we will of course end up in the other constructor. The code, as you can see here, is a bit redundant, so is it? Actually, it's not. We can add another variable to our class to see how this behaves. So int2 is, let's say, 4, 5, 6. Okay, and then let's inspect first the simple constructor case, this one. So let's get into it. Of course, it's a bit more code. As mentioned, it needs to allocate the memory and so on. Then we call the constructor. And the constructor here, basically it doesn't do much, it just does these two lines initializing the code. And when we inspect this constructor here, the way this works is, once we are in it, as you see, here we have our own code which represents the assignment, and then it has created a copy of the other code which just here it is the first thing. So here is our code that makes just the assignment, so we step through it, click, and then it has created some code which basically just does this one line. The things here are just shown because it kind of always just shows you code snippets, but really this is only one thing. So you see that in a way the code is a bit redundant, since the assignment for the second function will always be done anyway. So if you would have a lot of variables initialized like this, you might not necessarily want to do it. So there are ways how you can improve on your code. So you can, for example, call the other constructor first explicitly like this. How was that constructor? Yeah. I'm not sure if you can actually do it with the initialization list. Yeah, this does not work anymore. So let's first comment this use case out and then show you the other one. So that if you want to call the other constructor, you are not longer allowed to provide more entries in the initializer list, because that would kind of be at some point confusing. So basically I just telling this constructor to first call that constructor, and once this is done, do your own code, which in this case here does the same thing as when it was here, just that it's only allowed for non-const variables. So when we step through this, we have our call, and here when we go through this, we'll see that we will be we of course do some function prolog, then we do our call to the simple constructor, which will initialize both variables to the initial values, and then we will, once this is done, then do our own assignment. So in this case you are doing a trade-off between having more code or executing more instructions. So in this particular case, this does not looks particularly beneficial, because you kind of do quite a lot of more just to save on about how much is it, 2 lines of opcode, so it's not much. But if you would have like 100 variables and then always only want to assign 1 or 2 with special values inside of your constructor, that will of course be a more beneficial trade-off. Unless you are in a situation where you say speed means everything and the size of the code is completely irrelevant, then of course you would just go with the initial way how this was implemented. That said, of course, when you create a release build, the compiler might do many of its own optimizations, so the code might become a bit more convoluted and at the same time either smaller or more efficient, or both, depending on the your selection on which optimizations do you want to have. Of course, usually it won't be perfectly small and perfectly fast. That you can only say which of the both attributes the compiler should prioritize, and it will only do other optimizations if the prioritized optimizations are not in a conflict with this. Okay, are there any questions? Okay, I see there's a question. So the code of all the functions exists only once for the entire object. So if we have like our class and our variables, this getMyInt will only exist once, and the code, as we have seen, will just pass the object's address to the thing. The compiler will not create each time we make a new instance of the function or anything like that. Any other questions? Okay. No other questions, so let's continue. So the next very nice, very useful feature of classes is that we can extend them. So um, let's first maybe add a few more features to our class here, like something to set my int2. And as I mentioned, you can in principle write code directly here. So let's in this case do that. Oops. It kind of always wants to auto format it to be multiple lines, but you kind of don't want that uh, when you write code in the header. So for normal non-template classes, my recommendation would be if the code is trivial and fits in one or maybe at most two or three lines, it's fine to keep it in the header, but as soon as it becomes a bit more complex, you should definitely put it into the C++ file. And in principle, of course, you could have multiple C++ files. So we could create a very complex class and then split its functionality implementation into multiple CPP files. So there are no restrictions that all those functions belonging to this class must be in this one file. You can have just two files that are complementary. The only thing, of course, to keep in mind is you cannot have the same function twice. Then you will get a linker error that will complain that this particular function already exists. Okay, so we have made our class a bit more complex. So let's now create a second class, which will be derived from our first class. So this is a very important mechanism. See my class 2. It's a very important mechanism in C++ that you can create a whole hierarchy of classes with inheritance. So you, as you might remember with structs, we kind of did a bit of such a thing already just by putting a struct inside another struct, and then you have one struct that in a way combines the features of both, just that the access was not so very convenient, or that you could kind of make the same struct a second time, the beginning the same, and then add things and then cast things. So that would be more a hacky approach. But with C++, this capability has been formalized and is made very convenient. So we can specify here a base class to derive from my my class. Of course, you can just write those things manually. This wizard just creates a few lines of code for you. It's not something that would create anything in the background. So as you can see here, first let's move those things to our classes folder. The CPP file is again empty for now, and here it created a new class, and now it said public my class, and it included this other class. So it tells, it specifies how the existing members of my class should be accessible if you have an object of the my class 2 type. You could make the parent private or protected, or you could also derive a class from multiple other classes. This is something which many object-oriented languages don't allow. In many other object-oriented languages, you can have only one parent class, and that's that. And you are not allowed to create some class that would be derived from multiple parents. In C++, this is possible and works quite nicely. But of course, one, like with many advanced features, should be careful to not overcomplicate things unnecessarily, because then that of course gets in one's way. So let's include our other header file, my class 2, and let's try to create a new my class 2, and as you see, this in this case works okay-ish. So when we look on this thing, we can then see what it contains. But before we continue from this, let's add a few more things. So let's make another variable, my int3, my int3, 6, 7, 8, 9. Okay. So here we can open our should be called my class 2, of course. So when we look into our my class 2 object, we see it contains the new data, and then it shows us the other object from which it derives the data. And now we can also take a look how this looks in memory. I mean the reference on that, of course. And so we have 7. Wait, did we call this 1, 2, 3, 7, 8, 9? 2, 3, 4, 5, 6. But the other thing, this one says nothing. Then we should have let's just go with this value. So we are looking what this is. Yeah, hex is okay. Oops, no, I moved it. Let's quickly grab the right address again. Reference. Okay, so 7b, that will be our 1, 2, 3, which we had already. 7b. Then we have C801, that is this one. And then we have 1503, which is this one. So as you see, all those variables for now are just located one after the other in memory, quite the same way as it would be the case with structs. Just that it's much more convenient to access, because now, well, if we could access them because they're private, we could do it. But we can, for example, access the set, the getInt1, and we can create another set of functions. My int1 can create another set of functions on the other class to access the the my int3, get int3, zack, my int2, my int3, get my int2, get my int3, and voila, we can access both all the functions of all the classes. And we get our values 1, 2, 3, 4, 5, 6, and 7, 4, 5, 6, and 7, 8, 9. And now, of course, one might wonder what happens if we would create another get int2 class. For example, let's just go only with the get function, get int2 class, and let's always return the value multiplied by 2, for example. So let's see what happens, and here we get our normal value, and here we get, let's turn hex off, so we have 1, 2, 3, and here for 2 we get 912, which will be the 4, 5, 6 multiplied by 2. So we can in a way overwrite a function, but this is not quite the right way how you would want to do that. So if we create a pointer, my class 2, pay my class 2, and then create another pointer to my class 2. So we have 2 pointers to my class and my class 2. One thing is first interesting that we can just cast from a pointer to my class 2 down to my class 1. This works because, as you have seen, the memory layout basically contains my class 1, and then there are more things from my class 2. So using a pointer like this works completely okay. Now let's see if we read our value. Pointer to 1 from our pointer. I already have this pointer, so let's put this pointer here in the scope, that we don't get a complaint that it's already defined. And then we want, oops, to see what happens in the other case, my class 2. So here we get the pointer to the second class, and we run it. And even though, so this thing, when we can take a look here in this window, for example, And this thing, as you see, the values this pointers hold are identical. It's the exact same integer value, it's the exact same memory address, even though here when we call these functions, we'll see that one returns the original value while the other one returns the modified value. The reason for this behavior is that the compiler at the compile time looks which type does this pointer has, in this case this type, and then it will call the function, as you can also see here. It calls the function on this type, basically the defined one, and here it calls the function defined on the other type. So this mechanism of kind of overwriting things does not quite work. At least if you want the function to actually really overwrite it, in any case it does not really work. But first I will show you one more small change. So we can, if we change this to private and then try to compile it, this thing will fail. Because if something is private, it can only be used by the class itself and by nothing else. If it's protected, it is accessible to all the children. So here in the child class, we are not allowed to access my int2, but if this thing is again switched back to protected, we are allowed to access it. And there is also another mechanism where we need to compile it. And there is also another mechanism how we can allow also functions belonging to other classes to access those protected variables, but I will demonstrate this a bit later. Here the IntelliSense seems still a bit confused, but as you have seen, when it was switched back to protected, it compiled already quite correctly. So this behavior here, as mentioned, it depends whether you want it or not. If you always use the right pointer type, then of course it is not a problem. But if you would want, if you would, for example, have some thing that takes a function that takes a pointer and then calls our getInt2. So we can demonstrate this. For example, here int call getInt2. Oops. And this thing takes this pointer and then just, well, does it and returns our getInt2. Then you would have no way, in this simple way, to make this function somehow call this thing, even if we feed to it the right pointer. So let's make this example. So to b, we use getInt2. We feed to it the pointer of type 2, but internally it only has pointer of type 1, so it just does a cast and then it will still call the original function. And there are use cases where this is not desirable, where you would want to be able to actually replace functions which the parent class defines with your own implementation and have this being applied even when you call these functions on a pointer that is just of the parent type. And this can be done using so-called virtual functions. So here let's define those functions as virtual. And as soon as we do this, that will already start working. So now if we run the code, wait, must return a value. Right, this is of bold type and we have not used it before. Return true. I forgot that. Sometimes when you have functions in the headers and you never use them, the compiler will actually not compile them, so then you don't see the error that might be inside. But if you define the function as virtual, the compiler makes less assumptions about the use of the function, and then basically it assumes always it might be used, so then you will run in such a situation. Okay, but let's see here. So we have our 9 to 1 and again and again. So as you see, the virtual function now allows us to have the right function defined on your actual object called, even if you have a pointer that is only of the child pointer type. Okay, so let's improve this a little bit. Let's go to our class here. So here we have not written anything. We just by the just by the virtue of this function being defined as virtual on the parent class, the compiler knows what to do here. But if we want to be very explicit, we can add override this override keyword. This is kind of completely optional, but it is quite useful, because if you want to ensure that you override the function, if we just do this, it just allows us to create another function with the same name as exists on the parent. But as you remember, this function will not be called correctly if it's not a virtual function. And this override, what it does is it makes this fail if the function is not defined here as virtual. And as you see, we only have defined the int2 as virtual. So this is quite a nice mechanism to avoid accidentally thinking you have overrode a function, but in reality you haven't, and then you get inconsistent behavior, for example. So we have this here, and one thing that also might be interesting to demonstrate is how to call the original function. So it is, for example, a possible use case that you somehow want to override the behavior of your of the function, but you only want to extend it with something else, and then you would not necessarily want to re-implement everything. So you could just type let's grab the name from here, and one. So you just write type double point variable, and then it will, so you just specify the parent type, and then the compiler knows here it should call this myInt2 function, and then you can do something else. And it's important to know also that if a function is virtual, even if it's called from within your own class, so if you would add here a function, for example, let's do it here, int get myInt2 times 2x1, let's call it like this, and let's give it a body. So let's say this will just give us the multiplication of int1 and int2. So in this case you would say atom get my int2 time, of course, get time my int1. I think it was about 1. And now we can call this function from our class here, my int 2x1. It doesn't matter at this point which of the two pointers we take. Both pointers will have the things defined on the parent, and this needs to be int. And let's see how this behaves. So we already have checked that the code here behaves correctly. We see it here. So now let's step here into our function. So we have just a normal function call, and then we do the function prolog, and then we prepare the rest of the code. So you see here we prepare some memory, move there some variables, and then we call a function which is located at a particular place in memory. So this is how such a virtual function really operates. There is memory internally associated with the object, which contains the right function pointer. And what we basically do is we load the address of rex, and then from this thing we then take again an entry, and then we add 8. So apparently this will be the second entry. Yeah, that makes potentially sense. How many virtual things we have defined? Yeah, we have first the set. So set would be plus 0, and get is plus 8. And then the thing gets called. When we contrast this with the call here to our non-virtual function, you see that this is much simpler, because here we really just so let's see, we prepare the arguments, but we don't need to do those 2 lines before, and the call yeah, so the call is slightly more efficient, but of course then we don't have this nice feature that would allow us to uh, override functions. And then of course once we have the return value, we just do the multiplication and return it. So at this point, let's look how in memory our class now does look. So we can go to memory just of this, and we see that we have here our 7b. That was our this is not here. Yeah, so we have our C8101 1503 and F8. Why is this such a big number? Here we have our 7b. Let's quickly look what we have on our variables. So 1, 2, 3, 4, 5, 6. So now that should be fine. So 1, 2, 3 will be no, that will be here. Our 1, 2, 3. Then we have the next and the next values, and we have some memory at the beginning allocated. When we can see this here as well. So we see you have the variables, so they are kept in memory order, but here there is a pointer to something, and this something is a jump table, which, as you can see here, contains 2 entries. So we can, for example, we could use size of to get the size of our class before we make anything virtual, and you will notice that when we do it, when we make it virtual, the size of the class increases by, on a 64-bit system, it increases by 8 bytes, so basically by 1 pointer. And this does not relate to the count of virtual functions. So we can have 100 or 1,000 virtual functions, and the whole object still will have become only bigger by exactly 1 pointer. The reason for this is that these jump tables, which are created then by the compiler for these different child classes, they are then simply shared. So if we have multiple instances of our class, so for example we create class 2 and then we create class 2b and class 2c and so on, we can investigate that. So we have our class 2, our reference, and we have our first pointer 4 and another 4, so it will be somewhere here. Yeah, makes no, it's more, it's here. Wait, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, so it's only here. So this is our pointer, and we can get the same value, or if we just get the address. So let's clear this. My class 2 reference. We want this actual value, so let's say in 64, or just avoid asterisk. Now we want to see the value, so let's go with and to enable hex again, clear, and then we can go for B. We did not initialize B yet, so let's continue. Now it's initialized. B and C, and as you see, each object has its own memory address, which is individual and distinct, but all of them contain a pointer to the very exact same thing, this jump table. And we can then, if we go there, oh, let's keep it here. So void asterisk, we have a jump table, and if we specify that it's a pointer to a pointer, then we can get the individual entries. So we could do this 0, 1, and the next one should be invalid. Yeah, it just points somewhere. But the two valid ones that we have here, as you see, are pointing to our, in this case, function. So set, we have not overwritten, thus it remains the one defined on class 1. But get we have overwritten, thus it gets replaced, redirected to the one we have there. And for every potential combination, such a jump table is created. So we can, for example, create another my class. Let's be quick about it. Let's see, classes. Just oops, copy this. 3, and add it to our code. We just need to change, of course, this to be 3. And let's say that here, yeah, we don't change anything. This can stay as is. Here we need, of course, to rename this to 3, this to 3, and then just let's just multiply it by 3. Then we go to our class here, include the other child class 3, and now let's create an instance of the third class. Of course, have to change the name. Let's call it 3a. So we clear. So we again retrieve it from the C, and if we go to retrieve it from our A 3a, now we get a different jump table, and then we can investigate the jump table. So 0 is always the set into 2. 1 is the set into on 2, and then if we here use then the address of the other one, it's this one, so 0. The first function is again the same, but the second, 2 is not valid to 1. The second function is now the one defined on our third object. So this is how the whole thing operates under the hood. It simply adds one additional variable, a hidden variable, so to say, which points to the jump table, which is valid for the current object. And this jump table is then really set by the function, by the constructor. We can also take a look how this constructor behaves, but let's first add it explicitly. So here to our class 2, and let's steal from our class the constructors and destructor code. Of course, the names needs to be changed. We don't care for this case. Class 2, zack. And you could here use this double point my class 1 explicitly. Let's specify the value. Yeah, I still go with 1 to 3. What is this complaining? My class 2. My class 2, my class 1, my class 2. It doesn't have a 1, of course. The first one is without a 1, that's why it's complaining. So if you would have, for example, a class, or you would want to use a classes constructor, one which requires an argument, you could do it this way. If you want to use the default constructor without any argument, you can just keep this empty. Okay, so let's now step through this. So we put a breakpoint here and go. And then we step into it. So we don't need to prepare memory because it's on the stack. So we just directly start with the constructor. And let's just step here. So we call then the other constructor, the other function. Then we can exit from it. And then here, once we are inside ourselves, here we load ourselves, and then here we are setting this jump table pointer that applies to our new mechanism. So one thing, for example, worth investigating is how this whole thing will behave if we call a function from within a constructor or from within a destructor. So here let's also override for our second class. Then this one, let's bring them close together. So here let's also override this set ball, set my int 2. It's not const, so that should be right. Set my int 2, that was ball. Bool, virtual bool, set my, yeah, of course we also need the argument to be set. Tack. Yeah, now it's fine. The intelligence somehow is not very intelligent, unfortunately. So let's say that what we will do is we will divide this by 2. Divide equals 2, and then we will return set my int 2 on the parent class, of course. Yeah, so we could, for example, have such a functionality here. Actually, we could just do it like this. This is also nice. And then let's go to our class here, and let's add to it maybe a second optional argument, my int and my int 2. And then we'll use set my int 2. And let's say that in the destructor we want to set this to 0. It is not quite a useful use case, but just for the demonstration purposes. And so that we save on time, instead of stepping through everything, we will just add as a few lines which will print the whole thing. So let's include so that we can so that we have printf. This needs of course here a document now. And let's go to my class here, and we'll just always print the full function names. Of course here also need to add this include, so that we have our printf. Then with the destructor, then set my int we definitely need new lines, otherwise the whole thing will be quite unreadable. Set my int, get my int 2x1, and this we will move here because we want this the prints also in those functions. Oops. And so this is set int 2. Get int 2, and our class 2. For the 3 we don't care, we are not using 3, but here right in 2 set 4 5 6. Destructor, and then that's not right. This needs to be of course 2 as well. And get mine 2. Okay, let's run the whole thing. And for simplicity, let's see what of this we actually want to test. We would really want to just test the creation and destruction of the my class 2. So here just return 0 Okay. Now we already have this name my class 2. Let's comment this one out. Okay, so let's see. This is not quite as much saying as we want. Let's put this into brackets. Int x is equals. Okay, let's do it like this, and we put a breakpoint here. Right, and since it has a scope now, it's no longer visible there. So we are creating an object of the type myClass2, and as you see, it calls first a constructor for myClass1. Then inside myClass1, it calls myClass setMyInt. But as you see here, it does this using the setInt still defined on class 1. This is because class 1 defined its own pointer table, but it did not. It is not aware of that it will be a derived object. And then we call the constructor for myClass2, which would only then change this so that it will use the right function. So at this point, for a better demonstration, we could take this code here and go to our myClass2 and add it here. So this is the value we'd want to set. So here we can just keep this, for example, as 0. Let's run. And then we see that now from here, it still does one that we forget to rename this correctly. So we are in myClass2, set myClass2. myClass2 was virtual. Should be and this should in principle, let's see, so we are here in our function. We have prepared the we have to prepare the jump table somewhere. Class 2 2, so this should be the right one. Why doesn't this I think it wrote class 1. Maybe I just didn't look it's just where do we go to this set sure, because here we of course are setting the we are calling the set int 2 of the parent, and that's why that's of course correct. We don't need a breakpoint. Right, so we are in the one constructor, we do this, then we are in the second constructor, which then calls the second version, which then explicitly here in this line calls the first version. That's why we are back to 1. And then of course if we step over, we will see that it called getInt and getInt2. It was from this thing, and it here also first called our getInt2, which then implicitly called that the other getInt function. So we have this here. The getInt2 calls the getInt1. Sorry, the getInt2 calls the getInt2 on the parent class, and then now of course we can if we step further, we have executed the destructor. So as you see here, it called the destructor of 2, then it called the destructor of 1, and 1 again was only capable of calling its own function. So this virtualized mechanism, as you see here, it works when we are within a function that is called within the lifetime of the object. But when the object is being created or is being destroyed, then these jump tables are either not yet fully initialized or are in process of being rolled back. So you cannot rely. So for example, if there would be some sort of cleanup function that you have in the destructor of your parent class, you cannot override this cleanup function in a way that once it is invoked from the destructor of the parent class, that it will still use your override. This is a little bit inconvenient, to be honest, sometimes. But if you need such a functionality, it can be manually um, emulated, so to say. So what you can do is you could manually create a function pointer which you override, and which you then explicitly not reset on the on your own destructor, and then it will remain overwritten, and then the other cleanup function will be used. But this is of course a bit not elegant, so you should just put your own cleanup code here and make it such that you are not relying on invoking cleanup functions that belong to the parent class from within your own destructor. Okay, any questions? Okay, so if there are no questions, then let's continue. This we can remove because this is just for demonstration. Right, so let's take a look back on our pointers just to complete this part. So if we have a pointer of the type 2, we cannot sorry, if we have a pointer on type 2, we can easily cast it back to type 1. But if we have a pointer of type 1, we cannot assign it to type 2. Even though it's still the same memory, the compiler here only sees that it's the child class, it's the parent class. It does not know or track that the thing started its existence as a child class of type 2. So if you know that this is of the right type, then you can of course force the cast by telling the compiler that you know what you are doing. Qt, for example, it's a framework for C++. It offers mechanisms to validate whether those types are correct or not, and also modern C++ has an own casting mechanism that you could use to validate that such an operation would be allowed. But here, for now, we are just sticking to the basics. So, for example, what you could do manually, you could create on your you could create a function on your class 1 which will return you a value indicating the type of the class. So you could do that, my class, so virtual get type virtual int get type const return type 1. On 2 we define that this is a type 2, and on 3 we define that this is a type 3. One thing we haven't tried yet, but which we should try, is you can of course not only derive one class from multiple parents, but you can derive classes from classes which are derived from other classes, and so on. So you can have set a whole hierarchy of inheritance. You are not restricted to just one level of inheritance. So here we will soon create another class, but first let's do this. So we could have a code like get type is greater equals to question, or let's say it, yeah, depends. Then it does the cast, and else it just gives you null ptr, and then you would test if this is null or not, and then you can continue using it or not. So this is how one could manually implement a form of type checking. Of course, if you have a more complex inheritance structure, this simple mechanism wouldn't work. This would only work if you have only one branch. If we now derive something from like 3 it will actually be not even valid for 3 because 3 is already not derived from 2. So actually we should really check whether this is 2 and then that's it. Right, but now let's create another class which will be derived from a class which is already derived from some other class. See my class 4. Without the prefix here, we derive it from see my class 2. Zack. And our my class 4, then which will be derived from my class 2, we can quickly use it. We should also add some. First of all, we need to add this here. Oops. As an include, so that we can, so that we know that this thing exists, and then to this we will add some my int 3. Sorry, my int 4. In this case, my int 4, my int 4, my int 4, my int 4, my int 4 is let's go with this. Okay, and we can see here that our my class 4 then contains my class 2, contains my class 1, and that contains the jump table with the appropriate amount of entries. So we can make this really quite arbitrarily complex. Of course, one might also find such an approach a little bit unelegant, since it is, as said, a very complex. So there is a design pattern which is recommended to be used in such scenarios, which is also available in many other programming languages, so-called interface classes, or in other languages it would be just called interfaces, which would be a class which is only made up of virtual functions. It would not contain any own member variables. It would not contain any own functions. It would be just virtual functions, and those virtual functions can be implemented in a way such that they are not they don't even contain a function body. So let's create maybe such an interface. Just add another class. See my interface. Oops, my interface. Okay. So, and then we just start adding functions. Public, let's say int get my int 2, and add it into virtual, and is equal, and then we just write is equal 0, and we will not implement it at all. So now, having such an interface, we could, for example, go to our class 1 and say that it's derived from, oops, this needs to be included, hash. This is included from our interface, and then of course, like with normal inheritance inside of our where we are using this thing here, we can what is complaining, has no operator, doesn't not, that should be const. Now it will be fine. So having some class defined somewhere of some type, we just have our see my interface, path p my interface, oops, p my interface, then this equals one of our classes, doesn't really matter which, and on this thing you can then call the particular function. So this design pattern, as said, is not exclusive to C++. You can in many other language just define such interfaces, just that they are then it's like not class, but they are then type interface or however the other language operates. And you don't need to like set something to 0 or use virtual, because this is kind of implicitly what the thing does. And what then you can do, in contrary to multiple inheritance of classes, you can have an object which will inherit from many interfaces. So we have here interface, let's call this interface 1, and then let's add to it a make an interface 2 which only gets, okay, so let's say interface 1 makes getInt1, interface 2 makes getInt2. And this is kind of the design pattern. You would just, for every particular function you want to have, create such a individual interface. Class, so this here is derived from interface 1 and from interface 2. This needs to be virtual. No, this needs to override actually. So actually don't need to do anything. We're only working on the gets. So let's be more complete about it. Let's add the setter as well. Virtual set 0 get int 2 0. Okay, and then let's go here. Okay, these are without 1. Alright, and for the interface we don't actually need a CPP file, because it will never have a any functions. We can just delete it. One was without a 1, it was just like this. Okay, that should be fine. Not quite. Right, this is now called interface 2, and then we can of course derive interface 1, the same thing, interface 2, oops, 2, not 3. And on each of those interfaces, we only have the few functions that are defined. And the idea here is that when you're then implementing functions which take a sum of your objects which you want to be able to override, you would only pass an interface as an argument, and then you could have different objects derived from different interfaces still work in collaboration with your functions that you want to make flexible. So in principle we could now create a completely different class, something that is not related to our normal class, but let's be quick about it. Let's call this class A, and it will class A. We need to do a few renamings. So class A, class A, class A, class A. The rest remains. This remains. Let's just be quick about it. Just do it like this. Class A. Okay. And now we go here. So we create here class A. Class A, that needs of course to be included. Class A. And we can assign to the very same interfaces now from class A, even though A and 1 are not related to each other, at least not directly. The only thing they have in common is that they all share the same interfaces, and they don't even necessarily would need to share the same interface. So for example, class A could maybe only implement interface 2 and not implement interface 1. So we would have a function like this one that would then be called semi-interface. This must be interface 2 because we're using get 2. So this is boring. It will just then feed this thing with class 4, or with reference to class 4 of course, and or feed it with reference to class A. And this function would be able to do its work, whatever it is that it's doing, and the only thing that needs to be correct is this interface passed to it. This is a very powerful design pattern because it allows a very clean structurization of code, and to some extent also avoids complications if you would create various objects with multiple inheritances that might become very complicated. Also, you would need to ensure that you are not you don't have any variable name conflicts, etc. For example, if you derive from two parents, it would be inconvenient if both parents use the same own member variable. Then each time you want to access it, you would need to specify which parent's variable you want to access, and so on. And with interfaces, since the parents don't have anything, it is quite a clean separation. Any questions? Okay. If there are no questions, then let's continue. So let's see what would be a next good thing to show you. Right. So as you have seen, we can create our own functions on the classes. But what we also can do is we can create our own operators. So, for example, we could define what it means if we take what do we have here? What we could take? We have here multiple classes. For example, if we would want to define a semantics for this is equals this is a class free. Then let's we have an A. We make an A. Did not well, it doesn't matter. But we could, for example, still it doesn't matter. It means to have just a class 2 that's our A plus B. And so what this would mean? Well, first things first, what would this mean? And as you see, this does not complain. So this, the assignment operator is automatically created. We don't need to create our own. And what it really internally does, it just copies the object, which is not always what we want. So if we would have a pointer, for example, inside the object, like inside this string class I mentioned before, if the object is copied, we would not want to copy the pointer, but instead, at least usually wouldn't want it. Usually what we want is to create a new block of memory and copy its content to it. And here the thing is, of course, that the compiler doesn't know that we might want to do it, so it just naively copies the pointer. And we could, however, override the assignment operator with our own that would do exactly what we want. For other operators like the plus operator, there no default exists. Also, there does not exist a compare operator by default, even though one could naively think that a memcompare might be something that one could assume it would be a good first start of doing something. But as you see here, so is equals default compare operators do not exist. It's only the assignment operator which exists. And now, of course, the plus operator also doesn't exist, so we will need to create our own plus. So we go to our class definition, and then we write my class. So we return something of our own type, operator plus const reference. So we get the other partner for our plus operation. So the left hand operator is this, and the right hand operator is other. Where was it? I wrote this in the wrong place. It was class 2 here. So I said other is the right hand operator and this is the left hand operator. So here what we would do is we create a new object, red, that will be returned. Then we implement the operation. So for example, red punct, since this is on my int 2, so we'll operate on all the variables. My int 2 is, well, first things we could of course assign red to this. It would be a convenient thing to do. And then we say red punct my int 2 plus equals other punct. So we define here the semantics of our operation, that it should just make sums out of the individual member variables, and then we return this thing. So it's not particularly useful as a demonstration case, but it shows let's try it again. It shows what it does. Instead of x, and then we will see here that the values have been, as expected, added together. And such mechanisms of overwriting the operators are very powerful. In case of the mathematical operators, it's quite straightforward what you would use it for. You would use it, for example, to create an own class which can represent numbers bigger than, let's say, 64-bit. So if you would want to do some RSA cryptography before it becomes obsolete due to quantum computers, you could create an own integer, which is, for example, a 4000-bit large integer. And then you would implement all the operators. Internally, you would have some logic that breaks it down into, for example, 64-bit chunks, and then handles them in some intelligent way to emulate the operations on such large integers using instructions which can only perform 64-bit operations. And then once you have created your big int class, you can then use all the operators that you would want yourself, create plus, minus, multiplication, division, etc., whatever you need, and then use it really like any normal variable, as if it would be just a normal integer, even though there is now much more code behind it. But the more interesting thing you can do is you can also override the dot or the arrow operator, as well as the get address operator. So you can also create your own pointer types. So as we have seen in C, in normal C, pointers are extremely powerful and also quite dangerous, because you are not checking pretty much anything. You are just hoping that the code you write is correct, or you do your best to make the code you write correct, but there are no mechanisms, no built-in mechanisms that would in some way be able to verify that it is correct, or to help you with this. Now, having the ability to, for example, override the square bracket operator or the arrow row operator, you could, for example, create an own array class where you use the square bracket operator to access individual members. You could also override the operators for pointer arithmetic, so the ones where you are accessing the next or the previous member, and you could make all those mechanisms, all those features do some checks. For example, your class would not only hold a pointer to the array that you have created, but your pointer would also hold the count of elements inside the array. So whenever you do some operation, you could then check whether the operation will result in a valid memory access, or if it would try to access memory which is outside of the bounds of your object. Another useful case, for example, you could create an array which automatically grows when you try to access an element which it yet does not contain. So if you, for example, create an array with 10 elements and then you try to access element number 11, the code would see that this is not a valid access, but instead of somehow bugging out, it would then just create a bigger array, copy all the data over, and then give you a pointer to the new data. Now, the whole thing as is not fully foolproof, unfortunately, because if you, for example, would have taken a pointer to to something in this array, and then you do something that makes the array grow and make the old memory not valid. If this pointer is still around, the pointer will just become invalid. So if you want to do such things, you should either avoid the use of normal pointers entirely and use only such more complex smart pointers made implemented by you or implemented as part of the standard template library. And as just mentioned, such smart pointers, you don't need to write them yourself, or smart arrays, vectors. These are part of the standard template library, so we will be taking a look on those soon, and we will then see how we can um, reasonably create our own pointers just as a small exercise. Of course, normally I would recommend to just use the STL pointers because they are well tested and they cover all the different relevant use cases. Okay, so that much to these operators. What else would we want to try out? We have not yet tried to create something that would inherit from multiple parent classes, so we could create yet another class, actually two more classes, so let's do it in a more let's do it like this. Add class, see my class, how far are we for? So let's go with 5. My class 5, or let's go with, yeah, or let's call it my class B, that's nicer. Class B, and because we have like my class A is just a copy of my class 1, just with different names. My class B will contain my class B will be just its own class with a few getter and setter functions. Get int b. Oops. Okay, and then we'll create another one. See my class x. So we have a my class x, which needs to hash include my class a and my class b, and to be derived from see my class a and public see my class b. C. So my class x, first of course I need to include it. Oops. My class x, when you look into it, the dot operator, is it not happy? Yeah, it was a small typo. Zack. As you see, it contains my int 1, 2, and my int b. So it really merges together all the properties of its parent classes. One thing that one needs to be careful with this mechanism is that if we create now pointers to my class A and my class B. So when you remember before, when we worked with pointers to those classes that had a straight line of inheritances that only always inherited from one parent, those pointers they always had the same value. So if we knew that the thing also is the other type, we could just somehow now easily cast it to the other type here. the thing will change, because only the first parent from which we are inheriting with it we will be sharing the let's also make a pointer for this, only with the parent which so the same address is only valid for the first parent, and the other parents will be put later. So we could also add maybe to our class X also yet another own set of setters and getters. X, 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 okay. Okay, so let's see. So we have here 3 pointers, one of the same type. So this will be just a pointer to this, and then actually we could do it like this. That's nicer. And we'll see that one of the assignments will give us not the same value. So here, so we see this is our address where our class lives, and A is the same address. So those 2 pointers have the same memory. Of course, the semantics is different because it's a different type. But if we take a look on pointer B, we see that pointer B has some offset and points somewhere into our other things. So while we could easily force cast A back to X, if we try to force cast B back to X, we might get into troubles, and it will not do the right casting operation. We can try this out. So if we say X is equals B, so of course first of all the thing doesn't like it, and if we say that this is of this type and run it again, so we remember class X, P my class X and P my class A had the same value. Here now A has the value, so the values of course slightly change from one run to the next, but they should at least be the same values. And as you see, the compiler was intelligent enough to know that here we can actually demonstrate this even better. Let's do the same cast A and B, and let's give them own variables. So x1, x2, right? So when we run it and we look into the code here, the implementation of our first x1 is quite straightforward. It just takes the value and it just copies it over. But if we see what it does, if we try to do this here, what it does, since it knows that this thing, actually we should add one more test case, the one where the thing breaks. B A but this will always know that that is that. It's actually not that easy to break. We would need to have a pointer which knows which is of the parent type. And it actually is not that easy to break it. So let's just take a look through this, and then we ignore that. Okay, so I said this is quite trivial. The other one becomes significantly more complicated because it will need to find out the right type and give you the right value from the right value from memory. There are, I think, a few settings which influence this behavior, but generation. This we already have disabled. All options. Okay, so those things are disabled. So there should be not that much smartness. One simple thing, of course, to force the error is to just cast to void first, which strips the type information. Then we see that it does in both cases the very same thing. It just gives you the same value for both, and then of course for your x2 this is no longer valid. So when we look on x1, the correct values are those that we see, well, that's the interfaces that we see here. But if we do the casting here from the other pointer, because the type information was lost, we get some garbage data. But this is like very purposeful, so when we don't try to break it on purpose, it's smart enough to work quite nicely. Now one could of course also see how this would behave if B would be something that is only of type well, not of type X, but of type B. Let's go with new, or let's create a B, a semi class B, my class B, and let's just assign this here. So right here. So we see that the whole code still is quite complicated with some compares and some jumps. And here, but as you see here, it does not work correctly. So you can force such a cast, but it will not work since the internal structure is not compatible. So generally it is recommended not to use such casting operations without having some additional mechanism to guard this. And smart pointers, as available in the STL library, they have mechanisms allowing you to cast and do a check whether the type is actually compatible. So if the type would not be compatible, then the result of the cast operation would be a null pointer, and then you just check whether you got a valid pointer or a null pointer, and then if it's a null pointer, then you know that in this case something went wrong and you should not proceed with anything, with more things. Okay, right, so let's see what else would be worth mentioning. So one other thing that is also quite interesting is you can create, you can define elements on a class as static. So let's create another class. So my class, my class. We have here up to 4. So my class 5 in this case. Oh, we had a here. Let's move everything where I want it. So we have my class 5. So let's go with we need the public things, we need some private things, and let's say static. We'll make a pointer to ourselves. Oops. A static variable. And a static variable is one which is shared amongst all the instances of a particular class. So all classes of type, all instances of classes of type my class 5 will have the same memory for the my instance variable, and thus the variable needs to live somewhere. And usually you just pick a C++ file where you define the variable like this. Let's go with and so we still have the type. Then you have the variable. Actually, you don't need the type. I might need it. I need the type. So we have the type. Then you have the right name for the variable, and then you assign some value. And one thing which is often done with classes, if you only want to have one instance of a particular class, this is actually called a soliton, is to use such a static variable to track this one instance of your class. So we would have on public. So first of all, you would make the constructor itself private so that no one can create a new instance of this class, and instead you would have a function that you, for example, call instance, or you could also call it get me or something, but instance is like the common name for it. And this of course would also be static. And a static function on a class has the property that it cannot access any member variables except static member variables, because this static function is not related to a instance of the class, and thus it can be called even if you don't have any existing instance yet. So let's see so we have our class. We would check if this thing is null ptr, then we will make a new instance, our first and only instance, and then we always return the instance we have. And if we have one, then then we return it. If we don't have one, we create it and then we return it. And then we of course need to allow it to do something. So let's add a protected variable int my int. And my int 0. Then we have a normal here void get my int const return my int. There should be type, of course. Sorry, int. Of course, need to that's not the setup. We need the right type, right? And then when we are here, and of course we need to include this so that we can access it. And such a soliton would access see my class 5 instance get int, for example. So this way we will have one instance and it will exist for as long as our application exists. We might of course want to be able to remove it at some point, so we could add also a static void release or delete, you could also call it, but normally you call such functions that remove the objects release. And this thing would then delete instance and set instance to null, or null ptr. Yeah. The thing is complaining here about null because null is a preprocessor definition which needs to be somewhere included with some standard library, and here we actually have not included anything except this thing, so we can only do and use those things which are really just part of the language itself and not a part of any library that is around it. Right, so let's see. I can build it and it will work as expected. And since we are running out of time, I think this is a good point to finish for today. You have seen generally the main way how classes and operators and things behave. In the next lecture we will take a look on namespaces, which are quite also useful to structure your code in a more strict way. And we will take a look on class templates. So you might already remember function templates, and the same principle can be applied to an entire class, so that you write template type name t and then your whole class definition, and then this class will be implemented in a way where you replace types with template types that can then do whatever they want. So as a continuation of this, we'll then create our own C++ version of the simple list that you have seen in the last lecture, and this now will allow us to have a very nice comparison on how you do things in C and how you do things in C++. And for such a list, of course, it is very convenient to be able to create it as a template object, and this is quite a useful thing to have seen in practice, because a lot of container types provided in the standard template library, as the name suggests, are template based. So for example, the standard string template is made such that you have a normal string and a wide string, and they are just using type defs to specialize the string template, once for normal chars and once for wide chars. So the whole thing is quite flexible. So in principle, one could use this also to implement a string that would use 32-bit characters like it does on Linux, as you might remember. So are there any questions? Okay, so if there are no questions, then I think it would be good to think about some homework. Although I think at this point this would be a little bit difficult to do something very elegant. But one can go like, one can always invent some silly homework, and we'll do that. So from what's today, 07, 05, 2026, create a car with just a class car with virtual functions, get color, get color, int get wheel count, int get max speed. What else would you want? Ball is electric. Yeah, that's enough. And then classes then derived from the ccar class or an intermediate class. We can see car, old car. Yeah. Implement 10 classes derived from car, basically 10 random cars. Yeah. Yeah. So there won't be any set functions, just the getters, and you can implement intermediate classes, like for example a electric car, which always returns is electric as true, while the other old car always returns false, and then you can save a line or two in your further derived classes. It's not a very complex exercise, but at least it will give you some initial interactions with classes. And to make this not too short, let's add another component. Hold an array of type C, ccar, asterisk array of type C car 10, I think it would be the right something. So an array of C car pointers holding 10 instances of one of each class, then print all the cars in the array using a loop, a for loop, to the console using printf. Yeah. So when you run the program, it will just print out all the 10 cars it knows, and it will be quite a nice demonstration because we'll be using a lot of this virtual mechanisms. So you will have we could so maybe add a function which is which you could have as a we already have wheel count. So for example, wheel count does not need to be virtual because all cars have 4 wheels. At least all simple cars. You might of course have cars which have more. So I would recommend to keep all the functions virtual, but wherever it makes sense, you can just implement the function directly in the first parent class. Whenever it makes sense, you can have an intermediate class, like for electric cars. You could, for example, make the default car class always return is electric false, and then you have an intermediate class electric car which returns true, and then you implement the other details like this. And maybe one thing we can add here, color, comma, void set color, so so for the color, you should be able to set the color on the car. It should not be hard coded as part of the class, because like max speed, electric, wheel count, etc. These are like fixed properties. So you can have a function which just returns a fixed value. But for the color, since a car can have any color, you should implement it such that you can actually set it. Okay, any questions about the assignment or about the content of today's lecture? Okay, no questions. So let me quickly look in the calendar if there is one. I think the next lecture, yeah, the next week there is a holiday, so the next lecture is in 2 weeks from now on the 21st. Yeah, so that's that. If you have any questions in the meantime, you can of course email me, and yeah, and then have a nice weekend. Bye bye.